Ever get that feeling that different parts of your network are just speaking completely different languages?
Oh, definitely. You've got one segment over here humming along in OSPF,
Right.
another using ISIS maybe.
Exactly. And trying to get them to talk and, importantly, have reliable backups, it can feel like, well, like cracking some ancient code.
That's really the core networking puzzle we're diving into today. We actually got a great request from a listener about bridging these gaps.
Ah, perfect.
Yeah, specifically asking about getting an SPB fabric, using IS, to talk smoothly with networks running other IP protocols.
Well, consider this the decoder ring then. We're digging into ISIS external rate tests and use cases.pdf. It's by Ludovico Stevens from February 2018, version 4 specifically.
Right.
And our mission really is to pull out the key ideas on how to get this interoperability using this clever ISIS feature called external routes.
Think of it as a kind of universal translator for your network.
Yeah, exactly. Making things work together.
So just to set the stage, ISIS, that's intermediate system to intermediate system, it's a really efficient link state protocol.
Often found in SPB shortest path bridging fabrics, right?
Precisely. It's like the mapping system inside that SPB world. Helps devices find the absolute best paths.
Okay, so let's zoom in on this external routes idea in ISIS. That sounds like the key piece for translation.
It really is. Historically, ISIS was mostly focused inward, inside its own SPB domain.
Mm-hmm.
But external routes, which came in VOSS 5.0, let ISIS carry info about networks reachable through other protocols.
Ah, so OSPF, RIP, BGP, that kind of stuff.
Exactly. That's where the real interprotocol communication happens.
So ISIS learns routes from these other, let's call them network dialects, and then it can advertise them too.
Pretty much, yeah.
The document lays out some really practical ways this helps. Let's hit the first one. Connecting an ISIS SPB network to another IP network using redundant border routers. What's the main difficulty here?
Well, the big challenge, whenever you have redundancy, so like two or more routers connecting your SPB fabric to another network, say OSPF,
Okay.
is stopping routing loops. It's easy to get into a situation where one router tells OSPF about an SPB route, and then the second router hears that route in OSPF and decides to announce it back into IS.
Oh, right. And then your traffic just goes round and round like a network washing machine, as the document kind of puts it.
Exactly.
Yeah.
Not good for your data packets.
So how do we prevent that infinite loop? The doc mentions ISIS accept policies and these external routes.
That's the core of the solution.
Yeah.
It's about carefully controlling how routing information is exchanged.
So like one-way streets for routes.
Kinda, yeah.
Yeah.
IP routes get announced into OSPF, fine. And OSPF routes get brought into ISIS as external routes.
Okay.
But those ISIs accept policies. They're absolutely crucial for managing how those incoming external routes are treated, making sure we don't accidentally create those loops.
Got it. Now there's a note about compatibility, some older gear like VOSS, VPS, ERS series. What's the important point there for, networks with mixed equipment?
Well, the main thing is, while those older devices might live in an SPB fabric using external routes, they often just treat external routes the same as internal ones. They don't have that finer granularity of control.
So they can't really apply these specific policies we're talking about.
Basically, yeah. So the takeaway is you probably don't want those older boxes acting as your border routers in these kinds of setups.
Makes sense. You need the newer capabilities.
Right, like the VSP 4000s, VSP 8000s, ERS 8800s they used in the testing. They have the needed features.
Let's look at that test setup. VSTs, ERSs, some specific networks, 172.16.10.0, 192.168.20.0, mixing OSPF and SPB ISIS. What was the first problem they ran into just trying basic sharing?
The initial snag was default route preference. ISIS by default has a higher preference, meaning it's considered more trustworthy than OSPF.
So ISIS routes usually win out over OSPF routes if both are available.
Exactly. So imagine one border router quickly announces the OSPF routes into ISES. The other border router sees these new ISES routes. And because ISE has that higher preference, it might think, hey, this route learned via ISIS from my neighbor is better than the OSPF route I learned directly.
And then it stops advertising its own OSPF routes.
Precisely, which leads to an incomplete picture, maybe instability. Not ideal.
So one router kind of gets tricked by its neighbor. How did they fix that preference issue?
This is where that ISS exit policy is just, perfect. They set it up on the border routers to specifically change the preference of received ISIS external routes.
Change it to what?
To 130. Now, since OSPF route preferences are usually, between 20 and 125.
Ah, so 130 is worse than any standard OSPF route preference.
Exactly. Make sure the border routers always trust their directly learned OSPF routes more than the ISIS external routes coming from their border peer. It's like, thanks for the tip, neighbor, but I trust my own info here.
Smart. Way to prioritize local knowledge. And how do these OSPF routes look once they're inside the ISIS database?
They show up as external routes in the LSDB, the link state database. And interestingly, the original OSPF cost metric gets carried over as the ISIS external metric.
Does that ISIS metric matter much in this case?
It's there, but in this specific loop prevention scenario, the preference manipulation is the really critical piece. The metric plays a role for external routes, but less so here.
Okay. What about the other direction, sending routes from ISES back into OSPF? What safeguards did they use there?
Right. Got to prevent the loop going the other way, too. So they configured the border routers to redistribute only ISIS internal routes back into OSPF.
Ah, so because the routes from OSPF came in as external, filtering out external routes going back stops the loop.
Exactly. You ensure that no route that started life in OSPF gets accidentally sent back where it came from.
Clever.
And the doc notes the VSP 8000s needed to be OSPF ASBR's autonomous system boundary routers for this redistribution to work properly.
Good detail. There's also that quick note about a command syntax change in older VOSS for route maps. Just something to be aware of, I guess.
Yeah, syntax can drift between versions. Always good to check the docs for your specific software release.
But they also mention alternative routes causing potential trouble. What's that about?
Well, even with all this careful setup, the border routers might know some other way to reach a destination, maybe through a different path entirely.
Okay.
If the main ISS or OSPF route fails, these alternative routes might kick in.
Yeah.
But this could cause temporary flapping.
Flapping, like routes appearing and disappearing quickly.
Yeah. The routers might briefly start advertising routes back into the protocol they came from before things settle down. Potential instability again.
So even the backup plan could cause a mini headache. What was the fix?
In this specific case, the simplest, most effective solution was just to disable those alternative IP routes on the border routers.
Really? Just turn them off?
Yeah. It makes the routing much more predictable. Sometimes, simpler and more controlled is better than having too many fallbacks causing churn.
Fair enough. Better a clean, brief outage than constant instability. Okay, let's shift to route aggregation. Why condense ISIS routes before sending them to OSPF? What's the win for you listening?
Well, imagine your SPB fabric has tons of individual subnets, hundreds, maybe thousands.
Right.
If you flood all of those into OSPF, the OSPF routers might get overwhelmed. Their routing tables get huge, processing load goes up.
So aggregation simplifies things.
Massively. You take a bunch of those specific ISIS routes, say all the 172.next.x out of Pandeo 24s, and announce them into OSPF as just one single prefix, like 172.16.0016.
Ah, like summarizing a whole bunch of streets into just the name of the neighborhood?
Exactly. It makes the OSPF routing table smaller, reduces the chatter, makes the whole network more efficient, much easier to manage.
How did they actually set up that aggregation?
It involves a couple of things. First, prefix lists. These define the range of ISIS routes you want to aggregate. Their example was 172.16.0.016.
Okay.
Then they tweaked the route map that controls the redistribution into OSPF. They set it to match any ISIS internal route within that prefix list.
But instead of sending the individual route,
it sends only the summarized prefix, that 172.16.0.016 into OSPF.
Got it. But they also stress using black hole routes here. It sounds kind of bad. What do they do?
Yeah, it does sound a bit dramatic. But it's really important. When you aggregate, you're advertising a big block of addresses, right?
Like that 16.
Yeah. But maybe only some specific 24s within that 16 are actually active in your SPB fabric.
Okay, so what happens if traffic comes in for an address in the 16 that doesn't actually exist?
Without a black hole route, if you also have a default route somewhere, that traffic might loop around looking for a non-existent destination.
Ah, another potential loop.
Right. So you configure a static route for that aggregated prefix, the 172.16.0.016, pointing to null or black hole, and you give it a lower preference, meaning it's less preferred than real routes.
So it's a safety net.
Exactly.
Yeah.
It tells the router, if traffic arrives for this aggregated block and you don't have a more specific active route for it, just drop it right here. It stops the loop cold.
Like a dead end sign for non-existent addresses within the advertised block. Makes sense. Okay, last part of this first use case, injecting just a default route from SPB into OSPF, when would you do that?
You do this maybe if your SPB fabric is like the central core, the main way out to the internet, perhaps. And you don't want to burden the external OSPF network with all the details of your internal SQB routes. You just want to tell it, hey, for anything you don't know about,
send it to me, the SPB fabric.
Exactly.
Yeah.
Injecting a default route, 0.0.0.0 does just that. It's a simple send unknown traffic this way sign.
And the setup for that, similar process.
Yep, pretty similar. Uses a route map again. This time the map matches, say, any ISIS route, but then replaces it with just the default route before advertising into OSPF.
And I bet there's a black hole route involved here, too.
They betcha. A static black hole default route on the VSTA thousands, again with a lower preference than any real default route learned via ISS.
Why that extra safety step?
Well, imagine the SPB fabric loses its own connection to the internet. Its real default route disappears.
Right.
You don't want your border routers to keep advertising a default route into OSPF if they have nowhere to send that traffic. The black hole route ensures they stop advertising the default externally and just drop that traffic locally, preventing it from being sent into a void.
Okay, that wraps up use case 1 pretty thoroughly. We hit redundancy, loops, preference tweaks, aggregation, default routes. Lots of good stuff.
Yeah, a lot of fundamental techniques there.
Let's move to the second scenario. Routing between ISIS, SPB, and other protocols, but now with many redundant boundaries. What extra wrinkles appear when you've got multiple connection points?
Well, the potential for loops just gets magnified, really. Now, routes learned from, say, an OSPF network connected at one boundary could get advertised into the SPB fabric, travel across it, and then potentially leak out into a different external network, maybe a RIP network, through another border router.
Oh, wow.
And from there, it could even potentially loop back into the original OSPF network. It gets much more complex.
A real tangled web of routing possibilities. Sounds like we need even better tools to keep track. The solution again uses accept policies and external routes, but adds route tagging. How does tagging help here?
Tagging is like putting colored labels on the routes. It lets you mark a route based on where it originally came from.
So you know its origin story.
Basically, yeah. When routes from RIP and OSPF get redistributed into ISIS as external routes, they're given specific metric values. The example uses 172 as a tag for RIP routes and 192 for OSPF routes.
So the metric itself becomes the tag.
In this setup, yes, it's a way to embed that origin information. These act like those colored labels, letting the border routers know this route started in RIP or this one came from OSPF.
Okay, so you've labeled the routes. How does that stop them bouncing around between, say, the OSPF and RIP domains via the SPB core?
The ISIS accept policies on the border routers are now configured to look at these tags, these metric values.
Right.
So if a border router connected to the OSPF network receives an ISIS external route from its neighbor, and that route has the OSPF tag, metric 192.
It knows that route originally came from OSPF somewhere else.
Exactly. And the policy can then adjust the preference of that tagged route, making it less desirable, preventing it from overriding the locally learned OSPF routes.
And you do the same for RIP routes with the RIP tag.
Precisely. And then going the other way, when redistributing back out into OSPF or RIP, you use route maps again.
To filter based on the tags.
Yes. The route maps say, don't advertise any ISIS external route that has the OSPF tag back into the OSPF domain, and don't send routes with the RIP tag back into the RIP domain. It effectively stops those cross-protocol loops.
That's really neat, using the metric as a tag to track origin and prevent reflections. The doc also mentions testing failover. Did the redundancy work well in this multi-boundary setup?
Yeah, the design holds up. If a link on one border router fails, the redundant paths, managed by these policies and tags, take over pretty smoothly. Connectivity is maintained without introducing loops, even during failover.
Good to know. Okay, use case 3. Routing between two separate SPB fabrics, connecting two distinct SPB worlds. What's the suggested approach here?
Well, the document assumes these two fabrics are managed by the same team, same administrative domain.
Okay, so not connecting to a totally separate company's network.
Right, and in that context, they suggest using RIPv2 on the links connecting the border routers of the two fabrics.
RIPv2. Again, why not something like BGP?
They propose it as a simpler option for this specific scenario. Since it's all internally managed, the complexity of setting up BGP between the fabrics might be overkill. RIPv2 running just on those inter-fabric links can handle the route exchange effectively enough.
Simplicity has its merits. But wait, we've got redundant border routers in each fabric connecting to the other fabric, right?
Yep.
So loops again. A route from Fabric A goes over link 1 to Fabric B, then Fabric B's other border router sends it back to Fabric A over link 2.
Absolutely, that's the risk. And the solution probably sounds familiar by now.
ISI accept policies.
You got it. On the border routers, the policies increase the preference of ISIS external routes learned from the peer border router in the other fabric. Makes them less preferred than the internal routes within their own fabric.
Okay, stops the reflection. What about setting up these two separate fabrics? Any specific config points?
Yeah, they highlight assigning different ILA areas like 49.0001 and 49.002. Helps logically separate them, especially thinking ahead to multi-area SPB features. And of course, configuring the necessary BVDs, the backbone VLANs for SPB. Then the RIP config just goes on those specific interfabric link interfaces between the border routers.
So how do routes actually get shared?
Border routers in Fabric A take their internal IS routes, and maybe directly connected ones, and advertise them using RIP towards Fabric B.
Okay.
And Fabric B does the same towards Fabric A. Then, when a border router receives RIP routes from the other fabric, it redistributes those into its local IS domain as external routes.
So Fabric A learns Fabric B's routes as ICE external and vice versa.
Exactly. Provides that end-to-end IP connectivity.
And could you just send a default route between them if you wanted?
Yep, they cover that too. You can use RIP's default supply feature on one side and listen on the other.
So Fabric A could advertise a default, Fabric B could learn it via RIP.
Right. And again, best practice is to add that static black hole default route on the border routers as a safety measure, just in case the real default path goes away. Good old black hole routes. Okay, use case 4, routing towards a primary firewall. This feels like a super common need force traffic through one security point. Yeah. What's the challenge in a standard SPB fabric?
The main issue is how internal IP routes work with SPB. ISIS always wants the shortest SPB path.
Right.
So let's say you have a primary firewall and a backup, maybe secondary firewall, even if you want all traffic to hit the primary.
If the path through the SPB fabric to the secondary firewall's connection point is shorter for some node,
that node might just send its traffic towards the secondary firewall, bypassing your intended primary path.
Even if you try messing with the ISIS IP route metrics, make the primary path look better.
It often doesn't work reliably because the underlying SPB path calculation takes precedence for those internal routes. The fabric's physical topology kind of wins out.
So the fix must involve, let me guess, IS external route.
Bingo, you're seeing the pattern.
Huh? Okay, how does it work here?
You advertise static default routes from both the primary and secondary firewall's connection points into ISS as external routes. Okay, both advertising a default.
And here's the trick. You manipulate the preference when they're redistributed. The default route originating from the primary firewall gets redistributed with let's say a better preference.
Yeah.
Numerically lower value typically means better, but sometimes they use weight, which is inverse. The doc might clarify the exact mechanism, but the principle is setting one as preferred.
Okay, so the primary's external route looks more attractive initially, but wouldn't the shortest SPB path to the border router announcing that route still matter?
Yes, the SPB path to the border router itself is still shortest path, but the magic happens with an IS accept policy again.
Where? On which router?
On the border router connected to the secondary firewall. That policy is set up to look at ISIS external routes coming from the primary firewall's border router. And it increases the preference, makes it worse, those routes. So even if the SPB path to the secondary border router is shorter, the external route it learns from the primary's router is made less attractive by policy.
Wow, okay. So you make the route itself less desirable when learned from the wrong direction, effectively forcing traffic towards the primary path, regardless of the underlying SPB hop count to the border router.
Precisely. It's steering traffic using the external route properties, overriding the basic SPB path preference for that specific flow.
Very clever. Okay, last one. Use case 5. Routing between ISIS, SPB, and a BGPM PLS core using primary and backup paths. This sounds pretty high level.
Yeah, this gets into integrating with larger service provider or enterprise core networks. A key goal here is setting up resilience primary and backup paths without manually listing every single subnet in your redistribution policies.
Because that would be a nightmare to manage.
Totally unscalable.
Yeah.
So they look at 2 sub-scenarios.
Okay.
First is using GRT IP shortcuts, basically standard IP routing in the main routing table, combined with normal BGP practices.
Like using IBGP between the SPB border routers.
Exactly. The two SPB border routers peer with each other using IBGP. They also peer using EBGP with the routers in the MPLS core.
And how do you get primary backup?
Standard BGP attributes, usually local pref. You set a higher local preference on the primary border router for routes learned from the MPLS core. That makes it the preferred exit point.
And if that primary path fails?
Then the routes learned via IBGP from the backup border router become the best path, and traffic switches over.
And routes coming into SPB from the MPLS core?
The border routers redistribute those learned EBGP routes into ISIS as external routes. And crucially, you need an ISIS accept policy to reject any ISIS external routes learned from the IBGP peer.
Why reject them from the IBGP peer?
To prevent loops within the SPB fabric. You don't want border router 1 learning a route via EBGP, sending it into ISIS, border router 2 learning it via ISIS, sending it via IBGP back to router 1, who then prefers the IBGP route. You see the potential mess.
Right, stop that internal reflection. Okay, what's the second scenario? It mentions VRFs and a lack of IBGP support there.
Yeah, so this tackles the case where you're using VRFs, virtual routing and forwarding instances, maybe for L3 VPNs extending into the SPB fabric, L3 VSNs. On some platforms or configurations, running IBGP within those VRFs on the SPB side might not be supported or straightforward.
So how do you get primary backup and avoid loops without IBGP between the border routers and the VRF?
It requires a different kind of careful filtering. The border routers still peer via EBGP with the MPLS core, but within their respective VRFs.
Okay.
They redistribute those learned EBGP routes into ISIS, again within the VRF.
Still using external routes.
Yep. But the key difference is when redistributing back from ISIS into BGP towards the MTLS core. Here they configure it to only redistribute ISIS internal routes from within the VRF.
So because the routes that originally came from BGP were turned into ISIS external routes.
Filtering them out during the redistribution back into BGP prevents them from being advertised back to the MPLS core. Stops the loop that way.
And the primary backup path selection in this VRF case, how is that handled without IBGP tuning?
It relies more on the standard EBGP path selection and potentially having primary and backup physical links or maybe influencing metrics on the MPLS core side. It's a bit less direct tuning on the SPV side compared to the IBGP local pref method.
So two different ways to tackle that BGP integration depending on whether you're using the global routing table or VRFs and whether IBGP is in the mix.
Exactly. It shows how you adapt the techniques based on the specific features and constraints of your environment. Both really demonstrate how powerful IS external routes and accept policies are, especially when you mix them with BGP for these complex integrations.
Wow! Okay, this has definitely been a deep dive. We've gone through 5 pretty detailed use cases, all showing how to connect different routing worlds using ISS external routes.
Yeah, from basic redundancy to complex BGP peering.
The common threads seem to be managing route preference, using things like tagging, and being incredibly careful about redistribution to avoid those dreaded loops.
Absolutely. The flexibility you get with IS external routes combined with accept policies is really significant for building robust interconnected networks. But you have to understand those loop prevention mechanisms.
It's critical. So for you, the listener, digesting all this, think about your own network. Where do you face those tricky spots connecting different protocols or domains?
Yeah, and maybe some of these techniques, the preference adjustments, the tagging, the careful filtering with route maps and accept policies, maybe they offer some ideas or solutions for your own challenges.
It's definitely a complex area, always evolving, but hopefully exploring these practical use cases from the document has given you some solid insights and maybe sparked some new ideas for your own network designs.